All right, it's time. Good morning, good afternoon, good evening, everyone. Thank you for coming to Indoor Ag Science Café. My name is Cherry Kubota. I'm a professor at the Ohio State University. I'm also the director of the Ohio Controlled Environment Agriculture Center. So this monthly webinar, if you are new to this space, is something we do as a team, funded by USDA NIFA specialty crop research initiative. So thanks to USDA funding this, and then also thanks to all members who are participating in OptimIA project team for contributing to indoor agriculture vertical farms and the CEA at large. So I'm going to start a little bit of the update. So today we're going to have a special guest from all the way from Japan, but luckily she's in Guelph University as a visiting scholar this year. So she's going to talk about quite interesting topic. I will introduce her again at the end of this section. And then December, we have Dr. Roberto Lopez from Michigan State University. He's going to talk about temperature effects on crops grown in indoor vertical farms. It is part of sort of basics, indoor farming 101 type of presentation. So something to look forward. And then more talks will line up January and after. So typically we do Tuesday, 11 a.m. Eastern time. So as some of you know, we are developing OptimIA University contents, basic knowledge of indoor farming. We have probably 80% done. We still have several lectures to develop this by end of this year, but it has a lot of information, basic information. So if you are new in CEA or indoor farming, I think this is very, very helpful, including plant growing type of methodology information, as well as engineering and technology information. So I hope this is helpful. So there are multiple lectures we added recently, VOC, phytotoxicity, lettuce crop production methods, 3 lectures on economics, and then also humidity, and then microgreens. So check out our website, optimiauniversity.org, which is also linked from the project website for finding those lectures. All right, so today, again, we are lucky to have Dr. Shoko Hikosaka. Shoko is an associate professor at Chiba University and now a visiting scholar as a sabbatical leave. And then right now in Guelph, University of Guelph. And then she's gonna talk about how to grow strawberries and dwarf tomatoes for the production of pharmaceuticals and bioactive compounds. So something very unique. So I'm gonna stop sharing my slide and then have Shoko to start her presentation.
Thank you, Professor Chili Kubota, for the introduction and giving the presentation opportunity for today. Hello, everyone. I'm Shoko Hikosaka, the Associate Professor of Chiba University in Japan. Now, as Chili told, now I'm staying at the University of Guelph in Canada as a visiting scholar. My first professors are Mike Dixon and Thomas Graham. They are expert of the environmental control engineering. So today I'll talk about these topics in this order. So first of all, I would like to introduce myself. Our laboratory members are tackling several projects and research topics related to environmental control of plant factories and greenhouses. Today, I will introduce a part of them. First of all, I'd like to remind you of the popular modification technique of plants. This is a table of Sorry, I changed the pointer. Yeah. This is a table of modification technique mainly for the production of food, crops, and pharmaceuticals. I'll talk about for today GM strawberry for production of pharmaceuticals and genome-edited tomato plants for food production. As you know, GM plants have exogenous gene to produce targeted protein. On the other hand, genome-edited plants don't have any other exogenous gene and use their own gene. Few decades passed since the concept of plant-made pharmaceuticals, PMP, was proposed. PMPs by transgenic plants offer the following advantages over conventional production methods that use animals or microorganisms. So the main point is low-cost production and transportation. So low cost combination with animal pathogens, less concern for sterile environment. Environmental conditions for plants are easily controlled and no need for low temperature storage and transportation. And finally, no need for extraction process and injection. So presently, commercial production of functional protein by transgenic strawberry has been demonstrated in Japan. Of the two major methods of PMP production, one is a method using this stable transgenic plants, which involves traditional DNA modification for recombinant protein expression and relies on the generation of stable seed propagation. Also, regeneration is sometimes time-consuming. But the great advantage of this method is a stable expression and edibility without intermediate filtration or extraction processes when post-plants are horticultural crops. Another method of PMP production is this one, transient gene expression. This involves PMP production in plant tissues, which generates in recombinant protein rapidly within days without DNA modification of the host plant. Generally, Nicotiana benzamiana is used as a host plant. This method requires the extraction and filtration processes for obtaining the final products of the PMP. Presently, PMA production can be scaled up commercial level, and recently it has gained attention for producing a COVID-19 vaccine that mutates in a short period. This is a project list of the PMP production from 2006 to 2010, granted by Ministry of Economy, Trade and Industry in Japan. Several research groups, including our laboratory, have succeeded in introducing functional protein-related genes into rice, lettuce, potato, strawberry, and tomatoes 17 years ago. For both of pharmaceutical production methods, closed plant production system, CPPS, are beneficial for abiding by pharmaceutical regulations. For PMP production, closed system, also called a plant factory, or vertical farming are suitable for environmental control for stable gene expression in transgenic plants and cultivations. In addition, the transgenic plants should be cultivated in closed system to structure this to prevent gene diffusion. In this facility, all processes from cultivation to pharmaceutical production are completed in one building. From 2006 to 2015, our research group had investigated the optimal environmental condition required for efficient production PMPs using several transgenic rice and strawberries. This is a facility for transgenic rice production equipped with many filters and autoclaves to prevent gene diffusion. Transgenic rice for vaccine production has continued until now as a project of Chiba University currently involving our laboratories. Let's go back to GM strawberry production. In this project, we selected the commercial ever-bearing strawberry cultivar as a host plant. The most important strawberry attribute for cultivation in plant factory is a small, compact berry shape. In other words, high space use efficiency. In addition, so then light intensity is low as lettuce, and high demand. Strawberry has a high demand, so the established cultivation, we have the established cultivation technique, and the strawberry has two propagation methods, runners propagation and micropropagation. And strawberry has originally has a functional or sweet compounds. So on the other hand, the disadvantages are long cultivation period, a growth phase with two stages, vegetative and reproductive. And as a food set requires pollination, and edible part ratio is lower than lettuce. To accumulate a high amount of pharmaceutical protein in a food that prevent life-related diseases, we had studied about GM ever-bearing strawberries in a cross-plant production system. In this project, our co-research group had introduced human adiponectin, alpha-lactalbumin, and leucine, and dog interferon as the functional protein into ever-bearing strawberry. For example, this human adiponectin. Human adiponectin protein in blood is always circulating through our body. So when we have strawberry foods containing human adiponectin, the adiponectin concentration in our blood will increase along with immunity to lifestyle-related diseases. This is a cycle of GM strawberry production in a plant factory. To start the experiments with the same plant size and phase, we used micropropagated plant plants. And for the research, we removed all runners 2 weeks before flowering. To produce a high amount of pharmaceutical protein by transgenic strawberry at first, we had studied about the optimal condition for vegetative growth and promoting flowering and producing the fruits in a plant factory. The environmental uniformity and growth stage are particularly important considerations because cultivation period is at least 3 to 6 months longer than leafy vegetable production. In 2006, there was little information about strawberry cultivation in artificial conditions. So we started measuring the photosynthetic performance of strawberry plant in different environment conditions, such like that, using assimilation chambers. So in different environment condition involving variation in light, temperature, humidity, and carbon dioxide concentration, and so on. This is an example of fruit yield under varying PPFD and daily light integral. During this project, we often compare the performance of non-GM plants with that of GM plants. As a result, the environmental conditions for the vegetative stage and flower initiation in ever-bearing strawberry were the same between non-GM and GM strawberry. The left side result shows under 16 hours for the period, blue light enhanced flowering better than white and red light. And furthermore, the right side graph shows that this is a 24 hours light period, and higher DLI, white light, both white light and blue light, reduce the days to flowering. In PMP production, we prioritize the accumulation of the target protein over taste, color, and shape. Therefore, if a large amount of this protein accumulated on the surface of immature fruits, we will harvest a lot of immature green fruits with an even surface. This is because production efficiency is higher. In this case, we harvested mature fruits because the target protein content was maximum at this stage. As a result, 30 degrees Celsius of air temperature accelerates the fruit ripening without decrease of protein content. Therefore, this condition shortens the cultivation period and increase the production efficacy. It was unlikely that the strawberry would have tasted good. However, we are unable to verify their taste due to the guideline of the experiment during the research period. From a lot of experiments, spending lots of materials, funds, time, and collaboration with co-researchers and students, we could make this table. This is for human adiponectin gene expressing strawberry, but basic environment conditions for cultivation, ever-bearing strawberry may be almost the same. So you can ensure the modified condition to be optimal for the cultivar that you are going to use in the plant factory. This is the final slide for GM strawberry. Interberry alpha produced by the transgenic ever-bearing strawberry was approved for use in 2013 as the first example worldwide of drug produced using stable transgenic plants that has not been extracted or purified. So this is only one case of commercial production from this project. However, this is an important topic to break through the development of PMPs by plants. This result is an important first step both in terms of technology and legal development. Now, there are some strawberry plant factory for fresh food, non-GM, operating in Japan and other countries. This is Nishimbo Holdings is the oldest company started in Japan in 2011. This company used June-bearing strawberries. Nishimbo Holdings is a diversified company that handles chemical products, communication, and precision equipment. Now, this group continues to stably produce high-quality strawberries, and it is expanding into franchises in Japan. And second one, this is a recent famous company in the US, Oishi Farm, started by Hiroki Koga, a Japanese. He said on the website he wants to share the Japanese strawberry experience with the world. This company also seems to be growing rapidly by producing high-quality strawberry, mainly in New York. And MD Farm is another example of a company that developed and operated a strawberry cultivation unit in a plant factory and sell strawberry fruits year-round. I've heard that they have patented a method to continue harvesting year-round without a fluctuation of harvest. But that method is proprietary. There are also several other commercial strawberry plant factories in Japan because there is a year-round demand for strawberry in Japan. We all Japanese love strawberry very well, so the certain number of factories will continue to operate and expand. I believe that research and development will move forward with the aim of achieving higher quality and lower cost production. However, in the case of plant factories, both of lettuce and strawberry, the technology information is privatized, so it is currently difficult to make it a common technology. Therefore, university researchers do not conduct follow-up research and development on crops that have been stably commercially produced in plant factory. For the next topic, I'd like to briefly introduce the genome-edited tomato. So, genome-edited plant is a new breeding technique and has many advantages. You can make a high-value plant within a short time without transgenic processes, so it's easy to commercialize for food production. In addition, genome-edited plants can be cultivated even in outdoor fields. Therefore, at the moment, the most beneficial attributes in genome-edited plants are high value and the ability to be field cultivated. Japan population is rapidly aging and the market for food containing functional ingredients like a bioactive compound is expanding. Today, I'd like to introduce a genome-edited high GABA tomato developed at the University of Tsukuba in Japan. So GABA is an amino acid known as an inhibitory neurotransmitter. It has been reported to have an effect of suppressing the rise in blood pressure and relieving stress. So it is abundant in sprout brown rice, cacao, vegetables such as tomatoes and eggplant, and fermented foods such as natto and pickles. The research group of the University of Tsukuba modified a part of the GABA synthesis gene using genome editing technology to enhance its activity. The genome-edited tomato group shows 4 to 5 times higher GABA content of the wild-type tomato. The high GABA tomato is already being cultivated in greenhouses and sold by these venture companies. Maybe some people think is there an advantage to producing high GABA tomatoes in plant factory, which are already produced in a greenhouse at a lower cost than in a plant factory? I think it's a natural question, so I will talk about the possibility of tomato production in plant factory. Tomato plants also require long cultivation period like strawberries, but no special environment conditions are required to induce flowering. Therefore, regardless of the cultivar, tomato can be stably produced under the optimal condition for photosynthesis and growth with low cost even in greenhouses. It means there is less need to produce them in plant factory. Furthermore, regular tomatoes are tall plants, so they require a large cultivation space and three-dimensional lighting system. This characteristic seems to be unsuitable for production in plant factories. From this point, we think the way to make tomato plant factory production profitable is to produce high value-added goods within a short cultivation period and in a small space. Since 2021, our research group has collaborated with the Tsukuba group to optimize the environmental condition for dwarf type tomato in a plant factory. Now we are using dwarf tomatoes such as microtome, which are used as a model plant. But I hear from the Tsukuba group that highly functional dwarf tomato will soon be available for research. This slide is a part of our experiments. It shows that EPFD 300 micromole and recipe of 90% of red light and 10% blue light combined are suitable for microtome at the vegetative growth stage and shows improved radiation use efficiency, RUE, compared to the control. We believe that these technological developments have increased the possibility of producing fruit plants other than strawberry in plant factories. Many papers have been published on radiation and water use efficiency of plants so far, but from now on, space use efficiency will also be considered when we commercially produce plants other than lettuce and strawberries in plant factories. I think everyone is interested in the cultivation condition in plant factories, but I couldn't tell you all details due to the time limitation. So I prepared this table regarding the standard environment condition for experiments based on our previous results. This information has already been published in our papers. This is the lettuce and tomato and strawberry. Using these conditions as a control, we conduct various treatments depending on the purpose of the experiments. Based on the accumulated environmental control technique and knowledge in this table, scope of use plant factories has recently expanded further. The story suddenly jumps to space. With the promotion of the Artemis program, it is expected that about 100 to 1,000 people will stay and live in outer space and the lunar underground in the 2030s. Additionally, the Research Center for Space Agriculture and Horticulture, Chiba University, was launched in May of this year. The research members of our faculty are now developing the environmental control and gene editing or recombination technologies necessary for food production in space. This is known as lunar farming. In the near future, technologies developed for extreme environment are expected not only to contribute to the practical application of space habitation on the lunar underground, but also to be used as technology for food production, recycling, and environmental conservation on Earth, as well as for zero emission technology in agriculture and various industries. I know that this story about plant factory has gotten a bit far out there, all the way into outer space, in fact, but I will bring you attention back to this point. So we have identified suitable environment condition for BMP production by GM strawberries in plant factories. And environmental conditions are currently being optimized for genome-edited dwarf tomato with high level of functional compound in plant factories. These technological developments increase the possibility of producing foods other than strawberries in plant factories, producing food in outer space, and to zero emission production on Earth. That's all my information for today. I hope that everyone can look forward to the future use of the plant factories. Thank you for your attention.
Well, thank you very much, Dr. Hikosaka. I really appreciate Shoko-san. ありがとうございました。